Okay, so this is a new paper that comes back to this issue of whether we can extract fresh water in large enough quantity economically and um, also sustainably, and what would this look like with global warmings that are projected. So to start with, let's look at this schematic from Wikipedia, which shows a system of condensation where we are using some sort of a fan to blow out warm air, which is basically then sucking in moist air at one end with an electrostatic air filter, which is passed through an evaporator which has refrigeration, which is then flowing out back here into a compressor and the condenser. It's a regular cooling system which is going to squeeze out water vapor from the air that is being taken in, and it has to be moist air, which just means that the amount of energy that is needed to extract water from the air is going to depend on how moist it is, and that's always a big consideration as to how much energy it takes. And this is true for desalination as well. Desalination seems like a fairly well established, straightforward process, but in terms of energy it's still very expensive, and of course in terms of what we will do with all the salt that's left behind, the brine that's created when you remove fresh water from ocean water and desalination, that's going to add up very quickly if we keep doing desalination at larger and larger scales. These things of course have things like ozone generator to do the cleaning of the water before it can be pumped and then passed through the filters and provided as drinking water at the other end. The energy calculations are indicated this way, where we're looking at minimum energy requirement or least work, looking at the humidity ratio in terms of kilogram of water per kilogram of air that you can extract, and the ambient temperature. If saturation is high, of course you will have a lower energy demand in terms of kilograms per kg of air or water, but that of course depends also on then how do you transport that water, who has access, quantity, quality. Access are always big deal, are a big deal for water problems. But it's clear that most of the world is facing water stress, physical and economic water issues, and this shows that if relative humidity drops and you have high temperatures, then you will need more and more energy because you have to cool it, and you have to literally extract drops of water when the relative humidity is so low. Obviously, it's not a hard argument to make that energy considerations for condensation cooling are very high. Air is here. This is a system that is sold by a company called My3 Aquatech in India, which comes and establishes or implements or puts a system that looks like a refrigerator or a water cooler, which has a flow-through system. So air is drawn in through the air filter, moisture-laden air passes over the cold surface, condensed water collects in a tank. So the patented technology that this company has is some kind of a salt that is able to dissolve water in it, so basically using hygroscopic properties, and then that salt is recycled. So I won't go into the details, but then ozonization is done, collected water is filtered, remineralized, and passed through UV to clean it, and then you get drinking water. The capacity in terms of liters per hour, the cost, maintenance, etc. are going to be an issue as well. But I just wanted to point out that there is a system that's in the market in India, and there are many such systems across. There are many countries which are using some kind of water harvesting from the air to drive irrigation, drinking water, or other applications. This new paper, which came out in Science Report, which is a Nature franchise. Sorry, I forgot to put the link there. Let me put that and come back in a second. Hold on. Okay, sorry about that. So that's the paper that just came out from Praveen Kumar's group from University of Illinois Urbana-Champaign UIUC. To read the caption here, schematic illustration of our proposed approach for capturing moisture above the ocean surface and transporting it to proximal land for improving water security. So essentially their main idea is that there is always plenty of moisture supply above the air near land at the coasts, especially in the subtropics, where you can see that the moisture flux increases almost exponentially with height because the winds above the boundary layer begin to get stronger. But they're only talking about a structure that has a height of about 100 meters, typically a width of the surface that's intercepting the moist air is order 200 meter, so 100-meter height, 200-meter wide, and they say this is about as large as the side of a cruise ship, for example. So nonetheless, they imagine some active pumping system which is going to bring very high humidity air into this system where you are going to condense H2O, and of course they imagine using wind and solar renewable energies to reduce the cost as well. So this is the system. Evaporating moisture flux in the form of water vapor in the atmosphere above the ocean can be captured through an appropriately designed intake as conceptualized on the right, transported in the vapor phase through a conduit and condensed over land as illustrated on the left to obtain fresh water. The moisture flux increases gently with altitude due to higher horizontal wind, offering the opportunity to design vertical capture surfaces. The intake can be designed to optimize the moisture intake, taking into consideration the prevailing wind direction and its variation with altitude and time. So as you know, there are land sea breezes depending on day and night, depending on which way the pressure gradient works, low land heat capacity, heating fast during the day, ocean heating slower, so flow from ocean to land, and at night it's the other way, and so on. A compressor can increase the efficiency of collecting the humid air mass at the intake. As illustrated in the figure, renewable energy, wind and solar can power the intake, transport and condensation of moist air. We expect the intake to be located several kilometers offshore to ensure sufficient open water fetch isotropically around the intake. Well, okay, those are kind of idealized expectations, and actual implementation and efficiencies are going to be big issues, of course. And then they look at several large populated centers along the coasts over North and South America, Europe, Africa, Middle East, India and Australia. So you have the moisture flux shown here and integrated moisture flux. These are in millions of kilograms per meter per day of condensation surface, and the elevation is shown here with seasonality. And on this map you also have baseline water stresses going from low water stress, low to medium in the darker yellowish orangish colors, and getting to very high stress greater than 80%, where the colors are reddish. And Chennai is one of the cities on the Bay of Bengal which is well known for its water issues, for example. And of course in Africa you have plenty, and in the Middle East as well. So you can look at the various regions here and the numbers in terms of integrated moisture fluxes in million kilogram per meter per day. And what do you do with those numbers? Well, we will see in a minute the estimated water yields in terms of 300 liters per person in a populated center versus billions of liter in terms of just extracting in the given region. But nonetheless, you can see the seasonality, northern hemisphere versus southern hemisphere. You expect inverted kind of seasonalities in the subtropics. So basically they are focusing on the subtropics, where the downwelling branch of the Hadley cell and the drier regions, especially desert regions, create lots of water stresses, and they're expected to get worse with global warming. So here are the estimates. Assessment of the volume of annual water yield from a facility of dimension 210 meter in width and 100 meter in height, as I mentioned, placed closest to large cities in water stress zones, and the number of people it can serve to meet their entire need, estimated at 300 liters per capita per day. So you have various regions: ocean, sea and gulf, Persian Gulf, Balearic Sea, Bay of Bengal, Persian Gulf, Indian Ocean. So depending on the country, Arabian Sea. So Pakistan, India are of course highly stressed with population pressures as well. Red Sea, not so much population pressure, but just the desert. Same for Australia. Israel is doing very well with desalination up and down the coast, so they are always trying to squeeze every drop of water possible for agriculture and for domestic use, and Libya and Chile and so on. And the particular cities associated with them: Abu Dhabi, Barcelona, Chennai, Doha, Durban, Karachi, Lisbon, LA, Mecca, Perth, Rome, Tel Aviv, Tripoli and Valparaiso in Chile. So you can see annual potential yield in billions of liters per year ranges from as low as 37.6 here to as high as 75.1 or so in Red Sea, Saudi Arabia. Depends on the proximity to the ocean, the loading of water vapor in the atmosphere, and the details of how the pumping is done to the condensation system. Number of people served at 300 liters per capita per day. 500,000 here, as high as, let's say, in Red Sea, it's about 0.69 million per day, so that's pretty high. So the numbers vary, and you can of course have multiple systems to serve. So they are looking at fraction of the population that's served by each system. So 0.5 out of 1.45, for example, and for the what was the maximum here? Mecca, Saudi Arabia, 0.69 out of 1.58. Of course, Mecca is also popular for its annual pilgrimage, so that has to be considered in terms of transient population as well. Nonetheless, number of facilities to fully serve the city population needed range from 3 to 10 to 22 and so on. So they envision having multiple systems to meet the need of the entire population at 300 liters per capita per day with this system. And then they look at spatial variability of water yield along delineated near offshore regions of 200 kilometers across the world. The colors represent the annual potential water yield in billions of kilograms. They again show here the yield in billions of kilograms, 15 to 30 in some places. The yellow regions here, for example, 30 to 45. The bluest regions here, where it's warm temperatures, humid air, etc., can go to greater than 90 billion kilogram of water yield per year. Okay, so they are not small numbers. And then the map here is zoomed for each region: North America and Central America, Europe, North Africa and the Middle East, often referred to as MENA, and so on. So what do you want to do with these numbers? Obviously, you also want to see how they will change in the future. Again, looking at baseline water stresses that we already looked at, and they're looking at two scenarios for the future with historical estimates of integrated moisture fluxes from ERA interim or the ERA reanalysis. We didn't go into the details. Obviously, when you want to estimate the moisture flux, integrated moisture flux at global scale, you need data which is taken from ERA. And the future scenarios are the business as usual, so SSP 8.5, which will give us tremendous amount of warming, but it will come with more water in terms of millimeter kilogram, millions of kilograms per meter per day. So they are converting it basically into a unit. We can see here integrated moisture flux value is in million kilogram per day per meter width of an atmospheric column from 10 meter to 100 meter above the sea level. The details almost don't matter, but the point they're making here is that even in the most benign scenario, which is SSP 2.6, where the warming should remain below 2 degrees C with the 67% probability by 2100, will still give you billions of liters of water every year. Of course, you know that I'm not a big fan of these projections because model uncertainties dominate the first couple of decades, and then scenario uncertainties dominate the projections to the outer years. Nonetheless, keep the concept in mind, and the most robust argument being made here forcefully is that this is very feasible, sustainable, and cost effective. How does it become cost effective? The financial feasibility is looked at here. Having established that there is and will be sufficient moisture in the atmosphere column above oceans near coastal regions, particularly surrounding the water stress regions of the globe, we now address the question of the financial feasibility of the construction of such an infrastructure. Since no such structures exist, we do not ask what it will cost to construct such an infrastructure, but what cost model will make building and operating it feasible. Okay, so what will make it feasible to invest in such systems? In other words, can we characterize the upper bound of cost structure to be competitive with the current technologies, assuming that the marginal cost of water doesn't increase? So then you just compare what people are doing, like desalination, and then you say, how does this new system compare? We assume that the cost of building a facility for collection and condensation of atmospheric vapor is US $600 million, approximately that of building a large cruise ship or an oil rig. We further assume that the facility is amortized, so its value is written off over a 30-year period with a current interest rate of 3.75%, so you can think of it as a discount rate. We also assume a present-day operational cost of $175,000 per day with an inflation rate of 2.06%, so the operational cost will keep going up at that rate. The average in the USA over the past 20 years has been this inflation rate. Assuming that 500,000 people benefit from such a facility, the annual cost to build is $67 per beneficiary, and annual cost to both build and operate the facility is at $241 per beneficiary. In terms of the volume of water, this results in an annual cost of $2.20 per 1,000 liters of water, which is competitive with the production cost of desalination plants. That's the main argument. However, even after several decades of technological improvement, desalination plants have environmental effects associated with waste disposal. So getting rid of salt is a big problem. The desalination process produces a residual that is significantly warmer and saltier than that of the input. This residual is released into the sea, where it increases the salinity level and becomes detrimental to the marine ecology. In contrast, we believe that the process outlined here to capture water vapor that evaporates naturally over the ocean and transport and condense it to produce liquid water will have no significant environmental impacts in terms of byproduct generation. Of course, if you talk to social scientists, they will immediately start looking at who will have access to this water, and how the environmental justice and equity will be served, and how poor people will be affected by such systems, and so on and so forth, which are not addressed here. Only technical and economic feasibilities are considered, and you can take it for what it is and do further research if you are interested in this kind of direction. Okay, nonetheless, it's a new idea, comes from a credible group, so I just wanted to report it. Okay.